Here is the problem. We have a cylindrical tank with surface area A filled with water to a height h. A motor controlled by voltage U turns a valve through a gearbox. The valve controls the outflow. The goal? We want to control the water level h. The inflow Q in is a disturbance we cannot control. The motor relation is omega equals k times u. The gearbox reduces the speed. Phi dot equals omega over rat. The valve area A depends nonlinearly on the angle phi. A equals f of phi, read from a characteristic curve. The outflow is Q out equals A times V out, where V out equals the square root of 2gh. The tank dynamics. A times h dot equals Q in minus Q out. We choose states x1 equals h and x2 equals phi. Part A. Write the nonlinear state space model. From the tank equation, h dot equals 1 over a times the quantity Q in minus f of phi times the square root of 2gh. From the gearbox equation, phi dot equals k over rat times u. The output is y equals h. In state notation, x1 dot equals 1 over a times the quantity w minus f of x2 times the square root of 2g x1, where w equals q in is the disturbance. x2 dot equals k over rat times u, and y equals x1. This is our nonlinear state space model. Notice that x1 dot depends nonlinearly on both states through the square root and the characteristic function f. Part B. Find the set point. We are given Q in at the set point equals 50 cubic centimeters per second and phi at the set point equals 4 pi radians. At the set point, all derivatives are 0. From x2 dot equals 0, k over rat times u at the set point equals 0, so u at the set point equals 0. From x1 dot equals 0, q in at the set point equals f of phi at the set point times the square root of 2gh at the set point. From the characteristic curve, we read f of 4 pi equals 0.15 square centimeters. Now solve for h at the set point. H at the set point equals Q in at the set point squared divided by f of phi at the set point squared times 2g. Plug in 50 squared divided by 0.15 squared times 2 times 1000. That gives 2500 divided by 45 equals 55.6 centimeters. So our set point is h equals 55.6 centimeters, phi equals 4 pi, and u equals 0. Part C. Linearize around the set point. We compute the Jacobian matrices. The A matrix has partial derivatives of f1 and f2 with respect to x1 and x2. For f1 with respect to x1, the derivative of 1 over a times negative f of x2 times the square root of 2gx1 with respect to x1 gives negative f of x2 times the square root of g over 2 x1 all divided by a. Evaluated at the set point, negative 0.15 times the square root of 10 over 111.2 divided by 150. This gives approximately negative 0.03. For f1 with respect to x2, the derivative involves the slope of the characteristic curve df over d phi evaluated at phi equals 4 pi. From the tangent on the curve, this slope is approximately 0.06 square centimeters per radian. The result is negative 0.1332. For f2 with respect to x1 and x2, both are 0 since x2 dot equals k over rat times u has no x dependence. So A equals the matrix negative 0.03, negative 0.1332, 0, 0. The B vector is 0, k over rat equals 0, 0.5. The O vector is 1 over A equals 0.0067, 0. Part D. Compute the transfer function. Using G of S equals C transpose times SI minus A inverse times B, the matrix SI minus A is S plus 0.03, 0.1332, 0, S. The determinant is S times S plus 0.03. Multiply C transpose, the inverse, and B. The result is negative 0.1332 times 0.5 divided by S times S plus 0.03. That gives negative 0.0666 divided by S times the quantity S plus 0.03. This transfer function is the product of a first-order lag with time constant 1 over 0.03 and an integrator 1 over S. The negative sign means the system has an inverting characteristic. Increasing voltage decreases the water level, which makes physical sense since the motor opens the valve more, letting more water out. Let us recap. We modeled a cylindrical tank system with a motor-driven valve. Part A. We wrote the nonlinear state equations with states h and phi. Part B. We found the set point by setting all derivatives to 0 and reading the characteristic curve. H equals 55.6 centimeters, U equals 0. Part C. We linearized using the Jacobian. The key step was reading the slope of the characteristic curve at phi equals 4 pi, giving 0.06 square centimeters per radian. Part D. We computed the transfer function. The result is negative 0.0666 divided by S times S plus 0.03. This is a first-order lag times an integrator. 4 parts, 1 complete analysis, done.